Hello, my name is Juan Acevedo. I am resident doctor of ophthalmology at Clínica de Ojos Dr. Nano. Next, I will talk about the importance of visual access and pupil in multifocal lenses and about visual simulators. First, I would like to thank Dr. Bianchi, who invited me to give this talk and help me with the preparation of this topic. To understand the objectives of this presentation, I would like to raise a few questions. First, how do you select the best solution for each patient? I mean, what are the criteria we take into account when deciding which type of lens to implant to our patient? What does the choice of one lens over another depend on? From Pentagon, from the IL master, the patient refraction, the patient purchasing power, and last, who should take this decision? The ophthalmologist or the patient? My aim is to clarify these questions. You know, multifocal lenses have become increasingly common solution as alternative to glasses. That's why patient expectations are increasing all the time. But you must know visual quality depends not only on the multifocal lens, but also on the optical system. Now, let's talk about the optical system. At first sight, it looks complicated, but I will try to make it easier and more practical. I want to show you a video in which Dr. Sergio Bonafont explained in a clear way the optical system. The true optical axis is defined as an imaginary line through the center of the cornea, the center of the pupil, the lens, the rotational axis, and the fovea. All the images formed would be centered perpendicular to each other. This is an ideal optical system, but the human optical system is not like that. The optical surfaces are off-center, not rotationally symmetrical, and have a certain inclination in the curvatures. So all these images formed would be like this. A true optical axis doesn't exist. The optical axis is an imaginary line perpendicular to the cornea, passing through the nodal point and the center of rotation, but not through the fovea. It is temporal to the center of the pupil. The visual axis joins the fixation point with the center of the fovea. Its nasal inferior to the center of the pupil. Pupillary axis passes through the center of the pupil. It is perpendicular to the center of the cornea. These are the three axes represented in this image. The main line of gaze joins the fixation point and the center of the pupil. There are four angles, but only two angles determine the centering of the lenses. The angle alpha, which is formed between the visual axis and the optical axis. This is how they are represented on the retina. The angle alpha passing through the nodal point represents misalignment and asymmetry of the optical surfaces, tends to be more constant in patients. As a rule, the angle alpha is higher in children and hyperopic eyes too. To measure this angle, the eye trace workstation device is used, which identifies the optical axis located in the cornea and gives approximate values and are useful in deciding whether a multifocal lens should be implanted. For example, these angles less than 0.3 are suitable for multifocal lenses because they look through the center of the optic. Values between 0.3 and 0.5 should explain the risk of misalignment. And those with angle greater than 0.5 are not candidates for this type of lens. The angle kappa is formed between the pupillary and optic axis. Its normal value is less than 5 degrees. Patients with angle greater than 5 degrees may simulate strabismus. For example, positive angle kappa correlate with false exotropia, and negative angle kappa correlate with false endotropia. Well, all this in relation to pupillary size determines the optical centration of the multifocal lens. Pupillary size plays an important role in the relation of multifocal and IOL and is also of great importance in refractive surgery in the centration and the visual area. A pupillary size greater than 3 millimeters and less than 5 millimeters on the photopic condition is an ideal. The importance of this is explained by the area phenomenon, which relates the pupillary size and wavelength to size of this form in the fovea by the convergence of light. Varying pupillary size changes the sharpness and size of the iris. This explains why some patients with multifocal lenses, which are well-centered, have distorted reflections, such as positive dysphotopsia, which are seen as flashes, and negative dysphotopsias as shadows. This causes the visual quality to decrease and the patient is not satisfied with the result. This problem has led to the development of new methods to determine which is the best option for each patient. Therefore, devices were developed to allow the patient to really experience the type of correction that it is intended to be implanted. This enables him to experience different optical solutions prior to surgery. There are several types of simulators. The most classic and known by all is the photoopter. Based on this, more sophisticated devices have been created that integrate various visual systems and special lenses. Now, I want to talk about adaptive optics for visual simulation, a work done by Maria Viñas, an admirable scientist dedicated to the study of the properties of light, who already has more than 60 publications. The project is based on astronomical technology. Ground-based telescopes are capable of capturing short images of distant stars. Using waveform correction, this can be achieved. Adaptive optics has enabled advances in visual simulation through the study of the waveforms. The similarity from between the Earth and the eye has been studied to implement these techniques to improve retinal image capture. As we know, the image is for the convergence of light and the fovea. This would be an ideal optical system, but as we know, there are optical aberrations that make the image unsharp. These devices have the property to plot the optical aberration represented by wavefront through a sensor consisting of microlenses, achieving captures in the pupillary plane. These are the plots of the two planes, pupillary and retinal, in which all low and high order aberration are shown. The second component is a projector, which emits images onto the retina, integrated with the wavefronts already captures, and then reproduces by integrating these two properties, the image form in an eye with a certain degree of metropy. In this way, the device allows to reproduce the image as the patient would see it through the wavefront graft. In this way, the device allows to reproduce the image as the patient would see it through the wavefront graft. It is not possible to make an exact measurement, but it is possible to simulate the image perceived on the retina. The third component is an active optical element which manipulates the wavefront, correcting the patient's refractive errors. It can induce any pattern and modify the optical quality of the image. These elements are composed of an IOL in a rippling tank, a deformable mirror adapted to absorb voltage, a liquid crystal, a multiplexed opto-adjustable lens. This is same technology currently under development. These lenses can change their shape. All these elements are integrated in adaptive optic system. The image shows a supercontinuous laser source producing infrared and visible light measurements. The second is an adaptive optic lux composed with deformable mirrors and a wavefront sensor to measure aberrations. The third is a special phase modulator, which simulates refractive errors and produces very complex patterns. On the retinal camera for capturing all the images. And the last component is a psychophasis channel projects stimulate onto the retina. Adaptive optics also used measures contrast sensitivity, visual acuity, and accommodative ability. Not only correct aberrations, but also evaluate the process of brain adaptation to the different wavefronts. Single vision lenses do not induce significant changes in wavelength path and wavelength velocity. Blue light is focused before green light. However, with multifocal lenses, observe how the wavelength shifts in different directions, changing the order in which they are distributed. And this is important to understand. This is important to understand the process of adapting of new multifocal vision, which not all patients can achieve. This is a graphic representation of the image form with different active optical elements, which represent in a simulated way the visual quality of the patient will have each type of lens, both monofocal and multifocal, for forward, intermediate, and near. All these tests have been done in the laboratory to establish a standard response score and have been reproduced in human second-party cures obtained. Identifying similarities between the two groups, which makes it work reproducible. Back to the opening slide. The best solution is the one that the patient needs, according to his needs, his clinical and social economical conditions, his personality, and his visual optical system. The choice of one lens over another depends on the degree of satisfaction of each patient and the benefit to be obtained with each of them. Both, I think, the ophthalmologist and the patient should make the decision. Well, thank you very much.